Okay, class, so today I'm going to teach you about the ear. As I go through this diagram, I would like you on your packet underneath the eye diagram to label the parts of the ear. You probably won't have enough space to put definitions, so on your Padlet, write the definitions as I tell you what these parts of the ear do. So let's get started. What you're most familiar with is probably right here, this outside of the ear called the pinna. This is what we refer to as the outer ear. When we go to listen to something, sound travels through air, and it travels through our ear canal, which is our auditory canal right here. Everything that has to do with hearing is vibrations. So when the air or the sound travels through the air and hits the eardrum, it vibrates. Now your eardrum is protected by all the earwax in your ear. That's why you have it. It's a very sensitive place. So don't use Q-tips any further in your ear. Only use Q-tips on the outer ear. So as we travel into this middle ear, what we see is the three smallest bones. And these are the smallest bones in your entire body. You can fit all three bones on your fingernail. That's how tiny they are. So you have the hammer, the anvil, and the stirrup. And these three bones vibrate up against the eardrum, which is this right here, okay? And the air vibrates with the three bones, which are called the ossicles. And then the vibration of the stirrup hitting the oval window allows it to open, and the sound that you hear is transmitted from air into liquid. And so when it's in the liquid form through the oval window, it goes into the cochlea. And the cochlea and the vestibular organ, that is the inner ear. The cochlea is this snail shape, and inside the cochlea, on the base of the cochlea, is the basilar membrane. The basilar membrane has tiny little hair cells, and these are what vibrate in the liquid form. And that's how we hear. But then we still have to connect to the brain. So what happens is, from the cochlea and into the auditory nerve, we reach the temporal lobe, and that is where auditory hearing is processed. So that's a small version of this whole entire process of how we hear. Now, the vestibular organ, these vestibular sacs here, this is what helps us stay balanced. So if you're a dancer and you do 4 turns in a row, your vestibular organ would normally go crazy and you'd feel really dizzy. But that's if you didn't have it, but that's why it's there. That's what keeps you imbalanced. From your ear canal, there is a tube called the eustachian tube, and that's what connects your ears to your throat. So if you're ever thinking, well, why when I'm on an airplane do my ears pop? That's when the air in your ear canal and the air in your eustachian tube are not balanced. And that's when you feel the pop in your ears. So I want to show you a video that's going to take you into the ear, and it's going to show you what these pieces really look like.
The performance group Stomp celebrates rhythm. When the cast pounds on garbage cans or bangs their poles on the ground, they transfer the energy of their movements into energy that we hear as sound. Sound begins as vibrations that get carried to us as waves traveling through the air. The vibrating air spreads out through the theater and sets off a chain reaction in the ear. Our outer ear helps us locate sound. The shape of it might seem kind of odd, but it funnels sound waves inside. These sound waves usually hit one ear before the other, and this helps us determine where sounds originate. From the outer ear, the waves travel inside, where they strike the eardrum and rattle 3 little bones. The hammer, anvil, and stirrup are the smallest bones in our body. As they vibrate, they carry movement to the snail-shaped cochlea. About the size of a pea, the cochlea contains fluid that moves thousands of cells with special hairs. Rows of hair cells pick up vibrations and change them into electrical signals that get sent to the brain. These fragile cells are all that stand between us and silence. Over time, continuous exposure to loud sounds causes them to stiffen and die. Our ability to hear is more complex than we think. Usually, we hear dozens of sounds at once. Yet we're able to process them all and pay attention to sounds most important to us. Have you ever thought about lunch in a noisy room? This man is talking to his friend and listening to what she has to say. At the same time, he hears someone laughing, sounds of other voices, music in the background, traffic outside, dishes clanking, chairs moving. He's bombarded with sounds that his brain is able to filter. Our ability to handle so much information is extraordinary. We do more than simply take in sounds. We recognize them and often respond to them emotionally. Our brain has evolved to recognize the patterns and rhythms from all sorts of sounds. In fact, we make our own sounds and rhythms all the time.
I don't think there will ever be a day again in my life where I don't walk around and find rhythm in walking and breathing. And I mean, that's what it's all about.
On a side note, Stomp is a really awesome company. I've seen them before. At the end of this video, one of the dancers says to just listen to the beat of your own drum and always follow, what you want to do. So they're a really cool group. But moving on, we are going to talk about what happens when you might damage your ear. So again, this is all the information I gave you. This is the vibration of the ear and the path that it takes. There's the look at the basilar membrane on the base of the cochlea, and those are the hair cells with the liquid that move. This entire piece here is called the organ of Corti, and that is something very important to know. And then again, these messages then go from the cochlea to your auditory nerve and then your temporal lobe. Don't forget that everything passes through your thalamus, all the sensation. So we have three hearing theories. First, the place theory. Okay, originally suggested by Helmholtz. This is discovered by George von Bessky. And he got the Nobel Prize for this discovery in 1961. This theory is the ability to hear different pitches of sound due to location of the neuron on the basilar membrane in the cochlea. So you can see from this image that we have a high frequency here with the place theory. So the high frequency is at the basilar membrane, okay, and that's the place that the hair cells are. So how that works is there's a short wavelength and higher pitch. So the place theory explains high pitches. Problem is the place theory doesn't explain lower tones. So we need another theory. This theory then is the frequency theory. The vibrations trigger neural impulses to the brain at the same rate as a sound wave. Brain reads pitch from frequency. So lower frequency is fewer neural impulses, higher frequency is larger impulses. So this explains low pitches. So let's go back to that diagram, and you can see the low frequency is on the cochlea. Okay. So the problem with this theory is with pitches above 1,000 hertz, what do we do? So pitches above 1,000 hertz are too fast to read by the number of impulses. So you've got the place theory, you've got the frequency theory, well, we need another one. So now we have the volley principle. And the volley principle is similar to that of a volleyball court. The neural cells can alternate the firing and thereby achieve combined frequency with two different pitches. So with the combination of those theories, we've got place for high pitch, frequency for low pitch, and volley for middle pitch. What happens if you damage your ears or something happens and you can't hear? So there's what we call conductive deafness, and this is problems of conducting sound waves to the cochlea. So the eardrum